是啊，我们前面有点小技术问题，就连接的问题。现在应该大家能看到对吧？线上朋友们能听到吗？
Euh,
听到回个一。
je suis pas sûr que l'écran soit partagé. Un share
这个
screen.
屏幕能看到吗？也可以是吧？屏幕不能看到，看不到啊。non, il n'est pas écrit, il faut partager l'écran.
Ouais, mais je j'ai pas le contrôle pour partager l'écran. Non,
Voilà.
non, c'est ça, mais
Oui. Et ça, c'est un peu bizarre. 屏幕看不到。
peut-être ça. Ok.
啊，oui,
Alors,
ça revient.
donc
Oui, c'est de baisse.
comme ça,
Oui,
ça,
oui, je
ça,
pense.
ça suffit, ça?
现在有了。
Ok.
好，行，那我们现在就开始上课吧。就是我们
Ok.
这次课应该是这个星期有3次，我们这个月一共实际上是这个让方桑班的教授他一共讲10次了，主要是讲那个函数式编程，然后 Cog 和 Ocaml 都会涉及到一些，他应该会讲一些稍微基础一点，然后可能会讲理论的会多一点，因为我们这个课是中国计算机协会新化方法下面他搞一个公开课，然后下半年还有几位老师在讲那个线上的课，可能更偏应用一点。那么这个4月份这个课呢，可能更偏这个理论一些，涉及到一些类型理论的东西。那么具体的东西的话，我又不多讲了，一会儿那个让莫南教授他来讲，好吧？那么讲的过程中呢，就是大家如果有什么问题，可以随时我不知道是发消息或什么样，在那个框里面留言也可以，好吧？后面我们这边那个助教参然你帮忙，有什么问题你再随时告诉我们这边老师，行不行？然后我希望说我们讲的过程中还是尽量多理解一点东西，就说他讲的时候可以讲的稍微慢一点，然后嘛，I say that you can speak a bit
Slowly.
slower
Yeah, I
so that
try.
everybody can understand what you say.
Okay.
Okay, and we try to make sure that the majority of the participants they can understand what you teach. OK，
Okay.
好吧，那我们现在就欢迎这个莫南教授给我们上课。
Thank you. So I'd like to thank Professor Dunk for the opportunity to give you this series of lectures. So we have a long story of cooperation together, and so I didn't come here for 5 years already. So it's my pleasure to discover again the place here. So let us start because we have a lot of material to see together. So I will start with a short informal introduction on the objectives of what I want to teach you. And then basically what I will do is to present to you a number of Coq files, maybe from time to time also OCaml. I'm not sure. We will see, depending on time. Okay. So first, let me give. So if you want to find the material I will present to you, so you could go to my web page. So this is this one, but the easiest way to get it is to take your favorite search engine and then just type my name, Monin, M-O-N-I-N, the name of my lab, Verimag, okay? And then you will get my page. And well, maybe it's here. Yes, okay, this is my page. Maybe you can see it a little bit. And then you go to material for students here, okay? And basically, yes, you should get this. And I just opened a new directory here with this one, which is with a little bit of material. So it will be completed as far as we progress. So the current presentation is here, but okay. So maybe don't follow it. It's maybe better to follow on the screen. Okay. So this is the place you should get. Now, Coq is a tool for helping you to do math in mathematics in an interactive way. So it's good if you can, by yourself, perform the exercises I will present to you. So all my material will be can be followed step by step. So what you need is to install a number of things, basically Coq, the Coq proof assistant. Coq itself needs OCaml, a functional programming language. And of course, you need to edit files, and it's better to have a suitable environment to do that. So my favorite one is Emacs plus Proof General. So for people who know Emacs already, that's very good. You can learn it, it's not that hard. Or you could also use the Coq IDE, so you have to install it in that case. These three things, I mean Coq, OCaml, including Coq IDE, can be installed using a package manager devoted to OCaml, which is called OPAM. Okay, so you try to find OPAM. It's quite easy to install. So this is the way I know personally. I'm used to that. My own students, when I teach in France, use this, or they use another other kind of environment based on VS Code. I think that's the right name. I'm not sure. Okay, so depending on your taste, etc., there are a number of valuable options. Okay. So yes, when you install, you have the possibility. For instance, there is something called a Coq platform, which is quite huge, with many libraries for mathematics, for certified compilers, these kind of things. Of course, you can install them, but it will take much more time. For these lectures, only a basic installation will be needed. Okay, so not that large. Okay. So now some words on the objective of the course. So just a short introduction to introduce what is Coq.
You make the font a bit larger.
A bit larger, okay. Yeah. So please don't hesitate to interact with me if something is wrong. If you cannot see, if you want to ask questions, if I speak too not slowly enough or whatever, don't hesitate to raise your hands or something. So okay, so I can. This one is good. Okay.
Yeah.
Okay. So what do you prefer? Okay. So usually in this room you should be computer scientists or programmers. Okay. So usually the answer should be this one. But if you work in the academy, maybe from time to time you have to do that as well. Okay. So anyway, if you are in the first category, Coq is for you, because using Coq, though it's something for mathematics and doing things formal and very clean, very clear, it will help you. So it's like programming. It's quite like a game. You have to try things and see what happens. And according to the feedback of the machine, you progress. Okay. But anyway, if you are in the second category, Coq is for you as well, because you know, when you read or when you write proofs, supposed to be very good, in practice, there are many mistakes, small mistakes in the corners which happen because it's difficult. It's really a difficult task to think all possible cases, to think about all possible combinations. of phenomena which can be sometimes quite hard, and it is very easy even for very strong people to make a mistake from time to time. Even the greatest mathematicians are known to have been done some mistakes overall the centuries. Okay. So so when you check your proofs, your definitions, it's much more comfortable, much more safe. And now a number of very famous conferences, such as Popple, for instance, or others, like that people, how to say, give with a paper a Coq development, typically, or it could be another proof assistant sometimes to time, but Coq is quite is now a reference in this area. Okay, and I would add something that when you do math with Coq, it's become an IA. I didn't say AI, an IA. What is an IA? It is an interesting activity. Oh, sorry, it disappeared. Okay. Why? This is because when you write things in Coq, which are proof checked, which are at all the time. Okay, from time to time, it's quite easy. You write things, well, definitions, and of course, our first examples will be quite easy. The aim is for you to understand the concepts of Coq. I will not learn something to you about a new interesting theory. Okay, so very basic examples. So, okay, seems to be very easy. But from time to time, of course, this is life. You have to write things which are not so clear, and you could have feedback which are very strange. And that means that maybe you have to understand a bit more on what you wanted to say. Okay, so it is one very important thing. I will insist a lot on that. Is that whenever you write a single theorem, a single line, a single character, you should know why you type it. Okay, this is very important. Don't just try randomly some command, some tactic, how we know it. If you type at the end something called a QED, which means that the proof is terminated, it does not necessarily mean that you are done. Maybe you just perform something that you didn't understand, and later you are lost. So very important, everything should be understood. Do less, do few, but do it clearly. Okay, this is important. So myself, I will try to do the same. That is, you can find in the in the community a number of material for teaching many things, including Coq. And as the topic is a little bit difficult in some corners, it's difficult to. It's not that easy to teach, actually. Not that easy to teach because some very easy concepts need a lot of material, and it's sometimes we would like to use something which has not been explained before. That's not good. So that's why I call dark magics. So I will try to refine as much as possible to use anything which has not been completely explained before. I will try to use only really completely explain things, but not always. From time to time, I will say, okay, now I use that, and I will explain later what it means exactly. But okay, as few as possible. Okay, so that's all for this interesting activity, and. Okay, so the last remark, when you start to use Coq, it can become addictive. So don't forget to go to sleep from time to time. Okay. Now, what will I use? I will not rely on previous knowledge about math. Although Coq is something which is basically designed to write definitions, proof, and so on, so mathematical stuff. I will use intuitions for computer scientists, for programmers, even, okay? So I will use data structures, especially this kind of data, not arrays, but more binary trees or trees in general, lists, etc. Okay, and this will be used everywhere. For instance, one of the favorite examples I will develop will be AST, abstract syntax tree, so which is a basic data structure for reasoning on the structure of programs, typically. Text which are organized. Okay. Okay, so that's very convenient. I can correct my mistakes. So proofs themselves, usually when you see proofs, basically if you didn't use a proof assistant before, proof for you should be just a mathematical text. It will not be that. It will be something very well organized. A proof will be organized as a proof and exactly like a data structure. So we call them proof trees. It's a concept from logic, but anyway, it's very natural for computer scientists. Okay, and also the operational semantics will be also expressed. The semantics of programming languages will be also explained in terms of trees. So you see, this is something which is used in many places, and for sure there are other places for using trees in programs. Okay, not graphs. Graphs is something which is, I mean, the acyclic graphs, this kind of thing. This is something other. A tree is much more convenient than a general graph. If you go to graphs, you go to complications. So forget about graphs. Okay. My last introduction part. So Coq is a proof assistant, as I said before, and it is not based on set theory, so the basic theory that all mathematicians know, but it is based on something which is closer to computer science, actually, which is called type theory. Here, type theory. Okay, so type theory is a huge topic. So we will see, we only see the part which is needed for us, but we can see something which is quite old, actually. It is actually as old as set theory, but for some reasons, it was not as popular as set theory among mathematicians. It took a long time to have something effective. It took decades. So proofs. Okay, so you all heard about proofs. It's about mathematics. Okay. Okay, so you see that computer science. Yes, what I mean here is that computer science is mathematicians sometimes say, okay, computer science is in our home. Okay, it's a special branch of math. Okay, if you want. So okay, so this is just what I already told you before. I will not use intuitions based on any kind of math. You don't need analysis, geometry, or even set theory. Only things coming from programs, actually. Okay. So I think this is what I already said. I don't need to repeat it on this. Okay. Yes. See here at this point, we will use also intuitions coming from programming. So I expect you to have already some experience with programming, especially recursive programs. Okay, so I hope so that you are somewhat familiar with that. Otherwise, okay, it is an opportunity to discover that. So the programs we will talk about will be called functions. Okay, so why? Once again, it is because Coq, like OCaml, like other languages, so for instance, Haskell, another famous functional language. So all these programming languages are called functional programming languages. I will spend some time on this very soon. Okay, and the last thing which comes from programming is the type system. Okay. Okay, so what I said, okay, Coq is a proof assistant based on type theory. So proof is developed here. Now assistant, okay, it means what I already said, that is, it is an interactive tool. Okay, and the point is that in an ideal world, sorry, there are two kinds of tasks to be performed. Clever tasks for we, the humans, because machines are not supposed to be clever at all. Whatever you would think about the other AI, and tedious tasks. Okay, and it is very clear that tedious tasks you them, so they are for the machine. So basically, you enter inputs, and here you maybe sometimes you need to be creative to understand what is happening. Once again, you need to understand what you are doing. The machine understands nothing. The machine just performs some computations. That's all. And okay, but these computations provide you information. Typically, okay, your proof, for instance, is okay. Okay, your program is well typed. Okay, your program will terminate. This kind of thing will be checked by the machine automatically, provided you give the right inputs. Okay, and you have to know that, okay, it is checked by the machine, but who wrote the machine? Or, I mean, who wrote the proof assistant? Humans, basically. Or maybe they were helped by other software, but it's as you know, programming is an error-prone activity. So you could doubt. You could ask whether the proof assistant itself is good enough. And the point is that by design, a Coq is very secure. Not only Coq, a number of other proof assistants, for instance, Isabelle, which is one of the main competitors of Coq, it's also very secure. Okay, so by design. I will not enter into the details, but basically, the reason is that in such a big software, which the proof assistant, you have two parts. You have a part related to interaction, many small details which are not that important. But at the end, what you write is something which is expressed with a very few number of concepts, which can be explained typically on a page, on a page of paper. So which they are called the rules of the logic inside it. And inside all these secure proof assistants, you have a very reasonably small part, a few number of hundreds of code or thousands maybe, but not that large, which is very, very, very carefully written, which only checks what you have written at the end. Okay, so you have a number of things which help you to, for instance, to find proofs, etc. But at the end, everything will be checked by a very small part, which is called the kernel. Okay. Okay. So the kernel is really the thing which is important in all these proof assistants. Okay, so that's all for assistant. No question? And finally, type theory. So, okay, so I'll be very short on that. So type, you all know about typing, and you from time to time you use untyped programming languages such as Python, such as what Lisp, don't know what. The C language is, I would say, half typed. There are some parts which with types, but some parts where the type system is more or less broken. But in all in all typed functional programming languages, because Lisp is or Scheme are other examples of functional programming languages without types, these ones. But okay, so all the family of ML, such as OCaml and so on, the family of Haskell and Coq, and okay, so all these families of languages are based on a very strict, complete type theory. And what happens, you should know that from your experience, is that if the type system is not powerful enough, it is very annoying. There are some things you would like to write, but you cannot. You know that this program or this data structure works very well, but the types prevent you to write the way you would like to do because of the constraints are there. A typical language who had that is named Pascal. I don't know if you know this language. Okay, it is a language from the which was quite well known in the 70s, or maybe a bit old for you, but okay, it has been used a lot for teaching. Another language which is based on Pascal is called Ada, which has been was used a lot because okay, especially for secure things. Okay, so these languages, Ada is more powerful than Pascal, but typically Pascal was a competitor of the C language, and he lost because the type system of Pascal was not strong enough. But in the type language, we will see the power of typing is much stronger. So we basically you can write anything. Okay, so enough theory. So let us start with the main material now. So from now I will use a Coq file. So the rest of my lectures will be a kind of demo of Coq, step by step, introducing every notion progressively. So I use a style which was developed by Software Foundation. So Software Foundation is a very well-known website or set of material for teaching Coq, which is not that bad, but okay, well, most people prefer to present things with another. I prefer to present things in another way for reasons I could explain later. I think that Professor Dong agree with me that we can do better. But one good thing in software programming, Software Foundation is the way of teaching which is based on things that you can try by yourself. So I will use the same idea. Is it maybe I should make it a bit larger? Is it enough? Okay, but then okay. The problem, okay, then I will have to, because the problem is that the screen. So okay, so we will adapt when we progress. So the point is, okay, so I will show you what it looks like. Okay, maybe I can make this one a bit wider. So basically, you have three parts, and Coq IDE has basically the same presentation. You have this window where you write things, you tap your program, and you save your file. So this is the place of your file. And then you have answers in these two windows. We will see that when the answers will appear, because we have two kinds of answers. Okay. So I use proof general. So if you use Emacs plus proof general, here are basically the three keys you will need. So for instance, if I want to progress, I type Control C, Control N, and you see it becomes blue here. It means that it is accepted. It is just comment, as you can guess. Lines start, not only lines, paragraph starting with a parenthesis and one star up to the next star parenthesis, corresponding closing parenthesis, is a comment. I'll use 2 stars. This is for another reason, because there is a system which allows you to make a good documentation. So this is a kind of special comment, but okay, don't worry about that. It is just a comment. Okay, so let us progress. So the point is that when you write what we call a script, that is a Coq file, as in any program, what is written below depends on what is written before. Okay, so it is not allowed to change something before, because okay, imagine that you there is no whiteboard. Okay.
No,
Okay. Okay, so okay, maybe something it's more convenient to okay. So okay, so no problem. What did I want to say? Yes, okay. So the idea is that okay. So at the moment, don't. Okay. Imagine you write something. Okay, you go, for instance, up to this place. Okay, so at the moment, so I cheat. Okay, I go to this place. I type Control C, Control Return to say, okay, everything has been checked up to this point. Okay, and okay, so I put a number of definitions here or then, whatever. Okay, and then I change my mind. I say, oh, okay, maybe this maybe I should change this one. I don't know what it is. So assume that I change my mind at this place. So I say, okay, this is not a 6, it is a 8, for instance. Oh, okay, then you see that I have to. You could say that only up to this point it is accepted. After that, it is not accepted. I have to recheck what I did. Okay, so this is both interactive and very secure, because okay, so I can okay. Actually, 8 works as well as 6 in at this place, but okay. This is why you have this, and okay. So you feel very secure. So let us go to the so Control C, Control Return. Okay. Okay, and if you use, sorry, I am not able to have bigger characters on top here, but on the top of the window here, you can see a number of small menus, things you can tap there. So this is for people using Emacs, but on your favorite tool, you probably have the same. So for instance, here, if I type here, okay, I can see a number of possible things that I could do to, okay, the short keys I could use. Okay, I don't know all of them. Actually, a small number is enough. Okay, so let us start with an introduction. Okay, what I said here, I think, is the same as before. That is, it is a programming function, functional programming language. And okay, so it is both a functional programming language and a proof assistant. We will see the relationship between these two ideas, which is actually very close. But as I'm talking to programmers, so I will consider the programming part first. And actually, it is even for mathematicians, I think it should be the right way to teach Coq, because Coq is really based, the primitive thing in Coq is the programming language. This is really the primitive things. And if you start with the logical or mathematical part, very quickly, I think you will get into difficulties, because the way Coq is talking to you, the feedback of Coq, can only be understood if you know that behind that you have a programming language. You have something which is related to programming. So anyway, we are lucky. We are computer scientists, so we have an advantage. Okay, so I steam young because, of course, actually, Coq is used by mathematicians as well, and sometimes they want to recover their usual habits. And okay, but I think it's better for them to learn a number of things. Okay, so I will explain more on this when it comes on the screen. Okay, so I will consider two things: programs, but also I would like to show a number of small theorems about programs. And here I have a difficulty, which is that the basic theorems we would like to express on programs are based on equalities. But I think that we all have some intuitive notion of equality. And okay, even if so, the real thing behind equality is a little bit expensive in Coq, I would say. But just knowing two things about equalities will be enough for starting. Okay. Later, I will explain a little bit more on the status. So I will cheat a little bit with equalities, but not that much. I think it will not be difficult. So then, what is Coq? What is a Coq script? It is a sequence of declarations. You declare types, you declare values, and the functions are specific values. Okay, and then theorem statements and proofs. That's all. Okay, and this is organized using a number of things we know in programming. Okay, scope, mechanism, this kind of things. Okay. Last thing to know, basic thing to know is that every sentence we end with a dot. Okay, so if I switch to OCaml from time to time, okay, be careful, because in OCaml this is a programming language, so a number of detailed conventions are not the same. But okay, so anyway, in Coq, everything ends with a dot. Okay, so what? Okay, I go put this on the top. Okay, so I want to explain in a few words what is the essence of functional programming, if you didn't know about that before. So the first, okay, so I said that I will rely on your knowledge on programming, but please forget one thing. Usually you have a good practice of languages such as Python, C, or whatever, or C++, Java. All these languages are what we call imperative programming languages, which means that the main model you have in mind is a memory state, which can be small, but it can be huge, plenty of objects, arrays, bands, if it is a Turing machine, typically. So forget about this. If you remember of the very okay, once again, I would like to write thank you. Okay, so one of the important thing you have when you write imperative an imperative program is what we call an assignment. You all know that. So typically, I say v for variable is equal to, this is the syntax of a C language, or okay, something okay, like an equality, and then an expression. And then you go to the next assignment, and all this assignment will be inside loops, if then else, and so on. Okay. So here you see the memory part. The memory will change. Actually, this is not an equality. So this is a bad thing about computer science. The symbol equal does not mean equal. It means takes the value something else. It has something to do with an equality. Remember that, for instance, you could write v is equal to v plus 1. It is not an equality. Okay, it is not a fixed point of something. Can you turn my camera?
Yeah.
That is. Okay, that's a good idea, but I have to find the place to do that, and I am a little bit lost. Maybe this is here. No, not this one. Okay. Maybe
this one.
Okay, yes. I hope that it will not saturate the bandwidth.
Yes.
Okay, well, okay. That's okay.
Mm-hmm.
So this is the basic thing of imperative programming, the assignment, okay, which makes things okay. Okay, so we have the intuition of what it is, but it is very okay, dangerous at the same time. So you have two parts. You have the assignment with this part, and here you have another part which is called the expression. And one way of introducing functional programming is to say, actually, functional programming just only deals with expressions. You only use expressions, because expressions are made of, constants, operations such as addition and so on, and function application, basically. Okay, so just by applying functions to other functions, to other constants, variables, and whatever, you get something. Okay, so this is and this is enough to program, because of course we have recursivity. Okay, so we forgot about that. So we forgot about memory states, side effects, assignment typically, and we have only what I call pure expression. Pure means expressions without side effect, because in C language, typically, when you evaluate, when you compute an expression, this may have an effect, things x plus plus, this kind of thing. Okay, so you get the value of x, but at the same time you change x. Okay, so we have no side effect, so only pure expressions. Okay, and in particular, as the expressions are pure without side effect, you have a good byproduct, which is that the meaning of an expression is always the same. If you say, I don't know, x plus 2 somewhere, later in the program, x plus 2 means the same value. And you can put, you can say x plus 2 is always equal to x plus 2. This is wrong in an imperative setting, because in an imperative setting, the meaning changes with time, with computation. So here we have something which is very stable, so much more suitable for reasoning. And that's, in particular, it makes proving correctness of programs much easier on functional program than in programs. And byproduct is that computer scientists, very good computer scientists, wasted a lot of energy to make tools for helping people to have correct imperative programs. Okay, so that's life. Okay. So a particular expression is just a variable. You know what? No, you don't know what is a variable, but okay, it is a name. Okay, okay. Usually names are called variables. That's a standard name. So variable in imperative programming are variable. X means something, and then X means something else. It varies over time. But in math, variable don't change. Variable should be called invariable, but okay, that's a tradition. Sorry. So, okay. So in expression, you have variables, you have constants, and you have functions. And now the last two things is that in functional programming, functions are like anything, like in integers, like trees, lists, or whatever. There are values that can be put as argument of functions and input argument of functions, and they can also be, oh, that's funny. They can be returned as output of functions. Okay, so this is you have something similar in imperative languages. For instance, in C, you can play with pointers on functions, but it is a pointer on a function. It is not a function. Okay, I have not the time to develop that, but to some extent, you can simulate a function by a pointer, but not that much. Not that much. Here we really have functions which are very dealt with in the right way. Okay. And in particular, okay, so this is not mandatory, but in practice, all functional programming languages have this. We have what we call anonymous functions. So, you know, when usually in your private programming language, when you define a function, a subprogram, a procedure, I don't know the name, it could have, you give it a name first. You say, I declare the function f with these parameters and with that body. Okay, you always say that. Okay, but the first thing you give a name to your function. But okay, if you talk about something else, say an integer, you could say 3 plus 4. Okay, 3 plus 4 is an integer. I don't need to say, I call x the value 3 plus 4. You don't need to do that. So that's the same for functions. You are able to talk about, for instance, here, the function which takes the input x and return x times 2. This is a function. This is, I mean, this thing, okay, this is one of the possible notation you could find in math books. Okay, this is a function, and it has no name particular. I could say the functions multiply by 2, but I don't. Okay, maybe that's enough for me. I don't want to give it a name. So that is an anonymous function. Okay, and okay, this is because this is a particular expression actually. Okay, and an expression makes sense before we give it a name. Okay. Okay. A thing I would like to say now, which is not written here, is that okay. So I said that Coq and OCaml are functional programming languages. So there is a little difference between the kind of functional programming language we have in Coq and the one we have in OCaml. OCaml, like Haskell and as usual functional programming languages, are programming languages which are designed for efficiency. So when you write an OCaml program, you write very efficient programs. Okay. For Coq, it's not just, there is no point in Coq to have something very efficient. Usually, we are happy to make some computations, but it is not a general purpose programming language. There is a relationship. It is possible to write a reasonable function in Coq, and then to see, okay, I wrote this function, which is a little bit complicated. I could prove that this function behaves like I want. It returns the right result. I did proof using my proof assistant. But so what? Now I would like this function to correspond to a program, a real program I want to execute efficiently. Program extraction. Okay, I'll write this for in here. Okay. Program extraction. So which, okay, so from coq to OCaml. Actually, it is possible also to extract Haskell programs and other language. So this is a particular way of designing and writing program which is correct by constructions. So I write a program in coq or something which is more complicated than that could be explained, written in OCaml, but from this, so I will explain later, you extract an efficient program. There is a an excellent example of that, the project. So what is a COMCERT project? It is COMCERT means certified compiler. So it's the other order, compiler and certification. So it is a certified compiler for the C language, which has been written by Xavier Leroy, the main designer of an implementer of OCaml, by the way. So he at some point he decided to run coq, and so he has with of course with collaborators, he has quite a large program which is as efficient basically as a GCC with optimization. It is especially important for optimization because optimizations are a hard part and dangerous part of compilers. Okay, so with that, okay, he's able to have a very secure C compiler. Okay. Yes, last point. I think I find this interesting here. Maybe I should. Sorry. Yes, this is better like this. So you may still be interested in mainstream programming languages such as C++, Java, probably Python, and so on. And recently, I mean, in the past decade, the last decade, they introduced what they call a new, what is considered usually as a new feature. They call that lambdas. That's quite funny. They call that lambdas. Okay. And this is just something in order to allow inside these languages some kind of functional programming. Of course, you have to be careful because it is in an imperative setting. So, okay, so you have, if you use them properly, so without side effect, you have something which is quite similar to what you can do in OCaml, but it is okay, a little complicated. So what is funny is that this very name lambda, actually, it comes from the very root of functional programming languages. One of the theoretical basis, the main theoretical basis of OCaml, coq, and so on, comes from work of Church, along the Church in the 30s, so last century, before computers existed, actually. And he invented some very basic programming language called lambda calculus. So it was invented for logical reasons, okay? And in particular, he introduced anonymous functions, and these anonymous functions are written using the Greek letter lambda. So the funny thing is that the computer scientists which use this notion used a keyword like you know in programming. So the keyword is fun. Typically, fun introduce a new function. Okay, we'll see that very soon. But okay, so we call that fun, and people who don't know so much about functional programming use the original name lambdas. Okay. Okay, so anyway, if you understand very well functional programming here, you will be more efficient in interactive programming setting as well. Okay, now let us start the main technical part. So we will start with what we call expressions. A little bit, a little disclaimer. So at the moment, I will cheat a very little bit. I will use the expressions you already know using a notation you know typically. So when the square bracket is just okay, this is just for meaning. When you have square brackets like this, it means okay, some code. Okay, some code. Okay. So okay, so you all know what it means, enfin, usually. Okay, but beware that actually 2 and 6. So usually you think some integer, so something which is represented in the memory using 32 or 64 bits words, something like this. Okay, forget about this. It is just a number, a mathematical number, and Coq has its own representation and mathematically better of natural of numbers. And actually, these numbers are unbounded, for instance. So it is a little bit different from the int, and it is called nat for natural numbers. But okay, so I think it is mathematically very convenient. Okay, so we will use that freely, but as soon as possible, we will forget about natural numbers, or anyway, we will use them in a very limited way, which makes them not dangerous at all. Okay, and very soon we will use our own data structures. Okay, so first thing to know, in Coq, you can only, so the only expressions you can write are well-typed expressions. It's impossible to write. It's possible, but Coq cannot. You cannot become blue if you have something which is not well-typed. Could I give an example? Yes. Sorry. Okay, so I have to progress here. Okay, so for instance, the previous command here. Okay. So I say here check 6. So 6 is an expression. Okay, and here you have to look at this place. The answer here. Is it clear? Is it okay? The problem is now I have very little room here. Okay, maybe I will shrink this one. Okay, sorry, I have to go here. Okay, maybe I can. Okay, I hope that it will not be. Okay, so you have the answer here, which says that 6 has a type, not the type of natural numbers. Okay. Okay, so okay, just to explain that I could have well-type expression. I could type check 6 plus 2, for instance. That's okay. 6 plus 2 is still a nat. Okay, here on the right. But assume that we would like to check 6 plus. Okay, I will say true. You know what true is, but whatever it is not a natural number. So if I try this, sorry. Okay. So okay, maybe okay. I think that's okay. Okay, I will keep the check 6 here because otherwise he okay. So this is wrong. Okay, so here you see that the answer, so check 6 is okay, so it's blue, but now I cannot progress. So because I have a typing error, which is written here. Okay, I have to, okay, 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 not convenient, okay. Okay, so the full message, okay, maybe I can, oh, okay. Okay, I will make a copy paste of this one in this window here. So you can see it. Okay, this is just a copy paste. Okay. So the answer is the term true has type bool, whatever is bool. Forget about bool very soon, but okay. Why it is expected to have the type net? Of course, on the right of a plus, you are expected to put a net expression. Okay, so just to show you that only well-typed things makes sense.
Sorry, a very small question.
Yes.
So the warning message does not say the term 6 has type int while it is expecting to have a ball type. And the evaluations go from left to right instead of from right to left.
I'm not sure it's related to
it says that
yes,
there's a problem with true, but it's not a problem with 6. Yeah, if I do this, and what does it say?
No, the point is that actually the first thing he sees is a function symbol. I think he starts with plus. So of course, actually, okay. So the meaning of that, it is actually a binary function, which is addition applied to false and true, which doesn't make sense, of course. Okay, so the first thing it sees it's the root, the head symbol, the head symbol in lambda calculus, and then okay, from this, okay, now I am expecting I expect two things, two natural numbers on the left and on the right, and okay, so here he says, oh. But actually, he's talking about true. So, which means that yes, he's okay. He's looking at on the right first. If I correct this true, okay. Now, okay. Ah, sorry. Sorry. I should look at here. No, not okay. This is it was a copy paste. This one is wrong. So he start again with a true here. Oh no, he complains here about false. Yeah. Okay. So anyway, whatever order he complains about one of the, it is enough for one of the arguments to be wrongly typed, and then he.
Yeah, because that's always start from left to right or right to left. So it doesn't matter.
Doesn't matter. It does. Okay. Yes. I think like the typing rules are written, it is F applied to some. It could be from the right actually, but okay, okay. Okay, so only well-typed expressions are allowed, and once you have something which is a correct expression, like here, you can bind this expression to something, to your favorite name. For instance, here I wanted to bind this expression to this name. Okay, so I define a new thing called my typed 6. I say type because in my definition here, I provide the expected type. If I put another type, for instance, say nut times nut, a pair of two nuts, I think it will complain. Yes, here it says the term 6 has type nut while, okay, it should be that's times nut. So it is a way to ensure that you are understanding what you're doing. here we have two choices. We can also let Coq guess the type. I can be more lazy and write just that. Okay, so I'm like all computer scientists, I'm lazy, so I intend to not to write the types if it is not needed. So when you write a big expression, you have many opportunities to specify the types in many places. Okay, for in intermediate places. So at all places, actually, you can specify the type you expect.
And then the next question is, so what's the built-in types in code?
The
Built-in types.
The built-in types where?
What are the types which are already built in?
Ah, okay. So it depends whether you talk about bare Coq or Coq with the something which has been initialized. So bare Coq has only, okay, so just an answer for you, a prop set and the type hierarchy, that's all.
Okay.
All the rest is defined. So including natural numbers, typically, yes, okay. Yeah. So I told before that, so natural numbers are provided to you and they are mathematical definition. Actually, this is defined, they are defined in Coq. We will see that maybe tomorrow or in a few days, maybe, okay? I prefer to start with other notions because are not that interesting. They are needed, okay, for obvious reasons, but it's not that important to discover them at the very beginning. But okay, so they are part of the, how to say that, the preloaded library you have, basically. It's possible to remove all these initial imports. You can really play with bare Coq if you want. I never do that, so I'm not sure of the way of doing that, but it's possible for sure. Okay, and you could invent other notions of NAT, by the way, based on polymorphic lambda calculus, for instance. That would be possible. Okay, so I define that, but you could see that I did not specify the type here, so I'm not very I'm not very tranquil, how to say that still. So I check. So all the time, okay, so when the first basic command is check, please check, give me the type of expression. So my 6 now is an expression. I make a typing error, I mean mistyping. Okay, so this one does not exist. He says the reference my C was not found, blah, blah, blah. Okay, so because I forgot the X here, now this is something which has been defined. I can check it. And the answer is, of course, it is a NAT. Sorry. Okay, here. Okay, the reaction is a little bit inconvenient. Okay, so you see the ID on the right bottom. And defined 9 can be displayed. A name, not an expression. A print is not for expression, it is here. I can print my 6. Okay, and I see, okay, what is my 6 here? And I see on the right of the equal, this is a mathematical equality. It is 6. It is the body of the definition. Okay. We'll see other example now, but just check. But if I try to print my 6 plus 3, for instance, not, because I cannot print an expression. Does not make sense. I can print a name, the name of a definition. Okay. I could check my 6 plus 3. It makes sense. It is again an expression. Okay, so it has a type NAT. Okay, can keep it or not. But for print, it doesn't make sense. Only names can be printed, displayed. Okay, so now let's try a bigger expression. Say so my 6 plus 5 plus 2. Sorry, plus 5 times 2 with the usual priority rule. 5 times 2 is has a precedence over the plus. Okay. Okay. So I call it another NAT. Okay. So it just says that it is defined. And now, okay, I will display it so I can print it. And what you see here is the body of the definition. So if you know a little bit about OCaml, so okay, I will not introduce OCaml now in order not to waste my time, but if you know about or any other programming language, it does not make sense for a real programming language to keep the body. What happens in the kind of equivalent status? So okay, I will put okay. The material of this lecture here is on my website, and I have more or less an equivalent material written not in Coq but in OCaml. So you will be able to follow and see the little differences. I will not show here now because I don't want to complicate things on my screen. But basically, in OCaml, you would say something like this. I will write it here and remove it. You would say something like this: let another nat equal not okay, here it is colon equal, okay, it means equal by definition. I define something, it is okay. So in OCaml the notation is different. We use an equal sign, and we could write the same expression, okay. So in the ML file I wrote exactly this, okay, without a dot. But the meaning in OCaml is a little bit different. The meaning in OCaml is, okay, I will check this expression, okay, it will be an int this time in OCaml, not a nat, but an int, like, okay, and I will compute it. The machine compute it, and so it should be something like 16, okay, and the answer of OCaml will be not that another nat is equal to my6 plus 5 times 2, like here, but in OCaml you will see that there is sorry. Okay, the answer of OCaml will be not this expression, but it will be 16. Okay. Okay, because it makes sense in a programming language. You make the computation, and you don't want to keep. Okay, don't want to redo the computation all the time. In Coq is different. In a proof assistant is different. Okay, this is just an expression, and maybe I want or I don't want to compute it now. I just want to be able to compute it, but okay, there is no point to make the computation now and forget the original definition. So in Coq, the original definition is kept. Sorry. Okay, so let's forget about this little OCaml expression. Now, I could compute. So I will compute it here, not with the simplest way. There is another command we will see later. There are several commands for computing. Why? Because computing is something which is which is parameterized by a number of things, by the order of the computations, basically. So the order, when you have an expression, you could start to compute it from the left, from the right, from inside, from outside. There are many ways to compute an expression. You know that if it is a closed expression, I mean an expression only made of constants and functions call, if you have only this, the result should be the same, whatever the order. Okay, this is a basic thing you expect from an expression. So, okay, you have always the same result. So in programming language, okay, you just compute and get the result, and that's all. In Coq, that's different. You have things which could be partially evaluated or not, and okay, it makes sense because okay, we will see example later. The difference mainly is when we have variables. When we have variables, the computation can be partial in some sense. So what is important is the notion of what is called a strategy, an evaluation strategy. And so as we want to to make computation in an order or in another order, we may specify different strategies. So this is just the general idea. Just remember that for this demo, I will use a strategy called CBN. So this is something which comes from lambda calculus once again, which means call by name, and it is right strategy to be used for this demo. So so this is a strategy I will use, and in order to compute this expression here, I'd say eval. This is a command eval, like check or print. Then the strategy CBN. We will see other strategies later. In and my expression. So the expression here is just this name. So let us play. Okay, so I would expect to get 16. Yes, we got our 16 here. Okay, this is okay. See what OCaml gave you from the very beginning. In Coq requires two steps, an additional step. So definition and then compute. Okay, and of course I could evaluate not only a single name like here, but any expression. So actually, this is a body of another net here. So it is exactly the same. I have so this is a named expression, and this is an anonymous expression in some sense. Okay, here. So I evaluated, and okay, sorry, I want just to be sure. Okay, so let me type up and have my 16 here. Okay, so everything is as expected at this point. Okay, so until now I used constants 2, 5, 6, and used also binary functions, plus and multiplication. Okay, so once again, these functions, addition and multiplication, are preloaded when you start Coq. Okay, with natural numbers, we have a small library about them, including these two binary functions, plus some stuff for using them like we like, that is as infix operators. Okay, so now we will see how to define our own functions. This becomes more interesting. We will define our own functions, and here there is something new to learn. I mean, new if you are not used to the notation of functional programming languages, because function application is written a little bit differently for good reason. But okay, this is something which has to be catch very early. Okay, so we will discover that very soon. So we have seen expression, constants, etc. Names, okay, like my6, okay, and I had functions like multiplication, etc. Okay, so let us go to function now. Okay, so before going to function, so I will use something which is not available in OCaml. I will take about the body of a function. So the body of a function is an expression made of, like before, functions we already know, other names as already know. But, you know, say I may mention what we call variables. And it is possible to say, okay, let me consider something. Okay, this is here. Okay, I would be able to talk about some x. Okay, so I call it a variable. Variable means actually it is something I don't know. It is an unknown value. So not fully unknown. Actually, one thing I know, it's type. I cannot say a variable x dot. No, x has a type nat, so I have some information, but I don't know how much it is. I don't know whether it is 0, 15, or whatever. Okay, so in order to have a variable, I need to give it a scope. Okay, I don't want this variable to be available forever. Okay, so I have a scope which is defined by the section mechanism. So the section starts here, section. So I call it, this is my name, sec X. I could call it blah, blah, blah. Okay. I have to say here, end of the same blah, blah, blah. Okay. So end of sec X here. Okay. Well, it means that between here and there, the variable I declare will be available. For instance, okay, so X here is, I can see here, okay. Okay. So X is declared, okay, everything is fine. And now I could, for instance, check its value. No, check its type, okay. Okay, so I can check that X times 2 makes sense. It is a nut. Of course, I cannot say its value is, for instance, 0 or 10. I don't know. Let us try CBN. Okay. Okay. You see that Coq says that, okay, I have nothing to compute. Okay. Please don't play too much with my example. If you exchange the 2 and the X, you could expect that you have the same. It will not be the case because the CBN strategy may actually start to compute a little bit because the multiplication is defined in a way that makes it possible to start the computation if the 2 is in the other place. Or maybe.
No,
let us try. Let us try. We like to play. When okay. Okay. I get this. With CBN. With CBV, I want to show you what it will be with CBV. But okay, so okay, you see that it makes sense actually. Okay, 2 times X is X plus 0. So from this little experiment, maybe you could guess. Maybe multiplication is performed by looking at the value of the first argument. But if the first argument is a variable, it's impossible to progress. You can get this kind of thing. Of course, the right way it would be to print the definition of multiplication. Okay, but I will not tell you how to do this. Not now. Because in order to understand that, okay, I prefer to introduce the notion in another order. So, okay, I will use some basic intuition on numbers, but I don't want to show how everything is programmed. Okay. So just to say that I can talk about an expression made of constant functions, application, and variables, and to some extent I can get information and progress. Okay, so once again, X is an unknown but immutable or constant value. Okay, the name variable is misleading. You may think a variable, okay, it's vary. No, it does not vary. This X has the same, represents the same meaning, the same value between here and there. Okay, maybe later I may have another scope with another X, but I mean with X as well. If I introduce another scope with X, it will be another scope, another X. Like in programming, when you have okay, some scope and another scope, you can reuse your names, or you could have scopes inside scopes inside scopes, and you know that it is the last X which has been defined, which okay, so it is the usual mechanism of scopes we have in programming. Okay, but I mean in a given scope, X means always the same. It's invariable and mutable. Okay. Okay, so no memory state at this stage. So so why this? The byproduct of this, once again, is that you can, for instance, reason in a safe way. You know that X means always the same, so you can perform equational reasoning. Okay, no, with very easily in the standard way. I mean, like in math. Okay, so what I say, variables are invariable. Okay. And yes, the names are sometimes strange for historical reasons.
So when invariable within certain scope.
Yes. But even okay, if you change your scope, it is another variable. So anyway, it's okay. We should say the same written name means something else somewhere else. But okay, you only have to be aware of the scope. This is the only thing. You don't have to be aware on time or whatever, side effects, these kind of dirty things.
Because it's already over 10 seconds.
Okay, so thank you for pointing. So let me say if I have something to finish properly. Okay, we can make a break now. Okay, because we will see other nation.
We need to announce a 5-minute break.
5-minute break? Okay, so, I should write something?
You just say to the people online.
Okay, so have a rest 5 minutes.
5 minutes.
Merci. Did you understand me? That's okay. Don't hesitate to tell me. Please speak slowly, because when I am thinking, maybe I can forget to myself. So what is important is that you understand. Basically, understand what I am saying. So for me, it's not important. What is important is that you catch everything I say, especially at the beginning. Because if you miss the beginning, you get lost after.
Pas 100%. 90%.
Bon, par contre, après, ça va accélérer, c'est plus difficile. Bon, il faut pas que je perde les gens de la musique.
Mais tu n'as pas de temps.
Non, pourquoi faire?
C'est pas, souvent, on met des slides.
Oui, mais en fait, c'est vraiment à faire. Là, je peux éditer interactivement et je fais une erreur.
Oui,
En fait, oui, en fait, donc j'en finis un parallèle au KML et donc Grenoble. Donc pour KML, j'avais préparé des cours très très longtemps, 20 ans, j'ai des slides. Et quand j'ai commencé à enseigner le code, récemment, je sais pas, 6 ans, un peu comme ça. Et dès le départ, j'ai utilisé tout ça, le problème des modèles, et je trouvais ça beaucoup plus pratique qu'il fallait enfin, c'est pas très bien avec, donc c'est à la fois plus efficace. Bon, ça peut s'imaginer, le problème, c'est que dès qu'on veut changer un truc, il faut être sûr que ça rentre dans le code.
Mais normalement, il y a combien d'étudiants en ton classe?
50.
Ici, il y a sur la ligne, on passe à peu près 80 personnes sur la ligne.
Pas mal.
Ici, on a à peu près 20 personnes. Ensemble, on ressemble.
Oui, parce que ça peut faire, quand même. Bon, c'est bien que c'est toute la Chine contre les États-Unis, quand même.
那其他同学有什么问题？我们可以跟老师交流一下嘛，有什么问题可以随时提出来。我们尽量就是他讲内容中的说话，就是我们的上课内容。
On va prendre?
Oui, on va commencer.
So, time to continue the lecture. Okay, so I was just saying that what is a variable, it does not depend on time, etc. Okay, so this is the end of this comment. Next comment, defining functions now. Okay, so a function basically is introducing a new name like x and saying we want to make a function with it. So here you the syntax. I'm not sure that I'm okay. Okay, so functions are themselves expressions. This is why we call these languages functional languages. So okay, so typically, so consider functions that has input x and output x times 2. That's the same example as before. We will write this completely in this way. So this is a complete syntax. I mean complete in the sense that I put the type here. Okay. So I say it is a function which takes x as input and returns, so with a double arrow like this, written with the equal sign and the greater than sign. And here the expression, which means the result of the function. So expression to be evaluated once x has been filled. Okay. So this is the same function here, but written in a shorter way because here we can say that okay, we can guess the type of x. X cannot be, can only be a natural number because if you look at the right-hand side of the arrow on the body, you see that in order for this expression to make sense, to be well typed, x has to be a natural number. Okay, so this inference, guessing the type, is called type inference. Okay, so okay, Coq is able to perform some type inference. Not always. Sometimes you need to add some information because okay, it is possible to guess what it is. For instance, if I say just that x, I don't know anything about the type of x. Okay, so here Coq would not accept it. Okay, but here I would need to say, for instance, x is a nut. So by providing this expression, the type can be guessed. And okay, what about the scope? The scope is the body of the function. So x is available between here and by the end. When the expression is finished, okay, so x makes sense only in the expression here. Okay, so let us now check that we have a good function. Here return, okay, and we'll perform my favorite command. Check the type of this expression. Okay. Okay. If you don't have the computer, if you don't install Coq, could you guess what is the type of this function? What is the information which will be relevant to fully specify the type of the full expression? So I ask this because usually you think that your first thought is to say, okay, this function returns a nut, so the type is nut. It is a common mistake because actually the type should specify not only the type of the result, but also the type of the input. Okay, so actually, in order to specify the type of all this expression, you have to say it takes a nut x and it returns a nut. Okay, so the syntax here is this one. You can see here, nut, arrow, nut. This is the type of the expression. Okay, this is a simple arrow in Coq. And okay, if you think to OCaml, the type system of OCaml would use the same notation. You would say int, arrow, sorry, int. or we say sometimes into int, or here nat to nat. Okay, so the arrow means to. Not the meto, the TO. Okay, it takes a nat, returns the nat, and what could I say else? Ah, yes, in OCaml, you have almost the same syntax, but here the arrow is made is the same arrow as here. So, okay, so in OCaml there is the same symbol is used for two different things. Once at the level of types and at the level of functions. But in OCaml it is like this. Sorry, in Coq it is the double arrow here. Okay, so and we see that the type is okay. This is just what we said. Okay, and now as this is an expression, as usual, I can give a name to this expression. I can define mul2, for instance. I say that this name is bound to the previous expression. It is the function which multiplies by 2. Okay? And Coq just says, okay, that's fine. We didn't make any mistake. Here, okay. It is defined. And now, okay, it is defined. I would know what did I define? Okay. I check it again. The type is nat to nat. Here. Sorry. Okay. I say that here the type is nat to nat on the right, and as it is a name mul2 which has been defined, I can print its definition, and again we see okay here I can see that I see the body of the definition. By the way, yet another difference with OCaml, with any programming language. In a programming language, when you write the equivalent, which is let mul2 be equal to fun, blah, blah, blah. If you write this, OCaml will, or another function will compute something and make a kind of internal representation. And this internal representation forgets a number of things. It will be able to make the computation, but OCaml lose the information on how to print what you wrote exactly. For instance, you could write the same function with different names. You get that fun y 2y times 2, it's basically the same the same function written in different name, in a different way, sorry. And okay, but anyway, Coq keeps the original definition. It keeps something. And so when you so we are able to display it when we need it. This is important because sometimes we want to, for example, prove things, and it's important to be able to print the definition which was associated to the things we want to discuss about. Okay, so I am able to define a function. Now I want to use my function. For instance, how to use it? And basically, in order to use the function, you apply your function to some input, some natural input. So, for instance, 5. And here is a difference with the usual notations you know, except if you know about lambda calculus or Haskell or whatever, or OCaml, so that the use of parentheses is different. So usually, sorry, I try to have the full contents here. Okay, usually in math or in programming languages, you would write the name of the function applied to the arguments with within parentheses and maybe commas if you have several arguments. Okay, so please forget about that. Parentheses will not be used for that. Parentheses will be used only for one thing: grouping things together. Okay, so we will see later. Okay, so forget, and so we will just write the function followed by the argument. So I have a space here in order because otherwise it would be the name mul to 5. Okay, but no, it's mul to apply to 5. So I put a space, and that's enough. okay? No parentheses needed. So again, I can compute it here. So I apply multitude on 5. Let us see the result. I expect to have a 10. Yes, Cook is as good as me. Here, okay, so I got the 10. So everything is fine. And imagine now that I want not to use mul2, but its body, which is fun x 2 times x. It makes sense because, again, this is an expression. It is a function. And this function, I can apply it to 5 as well. Okay, so here you see that I use parentheses to group things together, because otherwise, if I remove the parentheses, it means something else. It means the function which takes x and returns x multiplied by 2 applied to 5. Yes, because here I have an application of something to something. Of course, 2 applied to 5 does not make sense. If I try this, okay, illegal application. Okay, I try to, okay, I make a copy paste of this. So I put it here. Okay, application non-functional construction. The expression 2 of type NAT cannot apply to the term 5 of type NAT. Okay, 2 is not a function. It is a NAT. It cannot be applied to a NAT. It does not make sense. Okay, so now let us recover what I typed at the beginning. So this is a function of type NAT to NAT. This is a function applied to NAT, and this makes sense. Okay, I got my 10 here. Okay. So I remove this. I would not be able to do this on these slides. Okay. So now what could I do? Yes, now I could do something, a new thing that I would not be able to do with the C language, for instance. I consider a new function. Okay, so let us focus on this expression here. So it is a function which takes an input f. Here I write its type because, okay, I want to be precise. It's better for me to be precise. Okay, I take a function of like mul2, okay, but it is f. I don't know what is this function. And I return this function applied to 5. Okay, like here, I had a function applied to 5 here. Or there, I had a function mul2 applied to 5. Okay, here it is f applied to 5, where f is the input of this function. Okay, so this is a function which takes f and returns f of 5. What is this type? What is its type? An idea? I know it is a function. So all this, all this. No, sorry. Okay. Sorry. No. Not f of 5. F of 5 is a NAT. This is the result. This is the type of the result. Okay. But now I talk about the whole expression. Okay. Let us this one. Okay. Not only the body here. I agree. The type is NAT. But now, sorry, fun f to f of 5. So the bottom line is as follows. When you have fun something, okay, let us call it okay, yes, okay, x, okay, x type 1, okay, it has some type, and I return an expression. Okay, so I will say that this expression has type 2. Okay. So the bottom line is that in general, of course, the expression may use x, but I don't care about it. I just say that, okay, I have an expression, maybe 2 or blah, 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 with x inside or not. Okay, but at the end, this has a type 2. So the full type of this is not just type 2. The full type of this is type 1, type 2, type 2. This is what you. This is the only thing you have to remember. Okay. So before I had this one, which takes a nut and returns a nut. Okay. So the type was nut to nut. Okay. Very easy. Now here we have f of type nut to nut, which returns f of sign, which is of type nut. So the result should be nut to nut. Exactly. Okay. So let us check. Right. Let us check really. Yes. Nut to nut to nut. And you see, pénible. Okay, you see the parenthesis, nut to nut in one block, okay, to nut. Okay. This is important. Okay, but now I have this expression. I can give it a name, for instance, just to okay. So I call this function up to 5. Okay, this takes a function 8 to 5. Okay, again I could check it. Okay, but the check will return the same type, nut to nut to nut. So I'm here. Okay, check up. Okay, again, okay, so everything is correct. And now I can do more, I can compute. And for instance, I had an f with this type, it was called the mul2, for instance. Okay, so let us apply this function to mul2, and I will get 10, as expected. Okay, I take the function which multiplies to 2 by 2 and apply to 5, it returns 10. Okay. Okay, so lesson 1, in a functional setting, functions can be input arguments of functions. Okay. Now let us consider the dual. Functions could be output results returned by a function. In order to do that, I will first consider the body of a function. So like before, I will use my section mechanism. Okay, so I say that the body of a function on the right of the arrow should be a type expression, blah, 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 blah. It can contain occurrences of its argument x, okay? But, okay, so we have seen that. But I could also have other variables which are available. So let me illustrate with an example. So I open a new section. I call it section n, okay? And introduce a variable n of type nut, okay? Some unknown number, n is declared, fine. Now I could check this new expression, the expression which takes x, sorry, the function with x, and which returns, okay, here I am able to have occurrences of not only of x, but also of n, because n is available. Okay? I am in the scope of n, so n can be used. So I use it on the right of my expression, of my body, of my arrow. Okay, and the result, okay, so just to check that it makes sense, because n is a nut, this is a nut, okay, because it is multiplied by 2. Okay, so you could see that Koch was able to infer that x has to be given the type nut, and with x of type nut, this is a nut, it can be added to another nut, and okay, so I get a nut, so I'll get a function from nut to nut. Okay, nothing difficult. Okay. Okay, so the point is that I can do that. I can refer to a name I know. Okay, so this new name has been introduced here in a section, but now I will write a function of n that returns this function. Okay, so almost the same trick as before when I introduced mul2. So I leave my section. Okay, and now I consider the function here which takes n and returns my previous function. It's the same as here. Okay, so I say that here I take an n and I return a function as output. Okay, so it makes sense. What is this type? What is this? The type of this thing. So the main thing is, so it takes a nut and in return a function from nut to nut. Okay, so the type should be so I take a nut and I return a function from nut to nut. So I guess that I put a check. Yes. So we will see how Coq prints this. Oh no! At the moment, at the moment I don't try it. We'll try it a little bit later. Let us check that I am able to apply this function to an input value 6. Okay, so if I apply this to 6, I get the type of the result, which is nut to nut. Okay, this is the application of my function to 6. So this has the type of the result of the function. The result is here. So the type of the result is nut to nut. Okay, and I see that. Oh, sorry. I got this function. Okay, so let us. Okay, I think is the example. So I do that. I will complete my my material here. So let us check the whole thing. Sorry. Okay. Before application, and Coq will say nut to nut to nut. So actually, this is the same as that. But there is a notational comment, sorry, a convention which says that when you read, oops, what did I do? Okay, sorry. When you read a series of arrows like this, it means that the parentheses are like this. Okay. So this is a function which takes a nut and returns a nut. So we will see soon why the convention is this one. Okay. So now, let me finish, or maybe I should put it here. Okay. So after I apply my function to 6, I get a function from nut to nut. So as it is a function, I can apply it again to something. So I will apply this to 5. Again, I put parentheses like this. I put parentheses to to show to explain what I want. Okay, and the result is 16 as expected. Why? Yes, because 6. So n has the value 6. Okay, so here I have a 6. So I get the function which takes x and returns 6 plus the double. And then I put x, so it will be 5. So the double of 5 is 10. So 6 plus the double of 5 is 16. Okay, so nothing difficult. So now, parentheses. So what I said is that this thing actually can be written function applied to 6 and applied to 5. I wrote this to be clear, but I can write like this. Okay. So we'll see soon the shorthand for this one, but I say the 6 and the 5. So you see that actually this acts as a function of two parameters. This is a very point. A function with one argument, which returns a function with one argument, is really like a function with two arguments, but the two arguments are provided input one by one. I could consider separately this, okay, I give only one argument first, okay, I have the right, it makes sense, okay. This is what we call sometimes partial application. I have a function and I play it once, but actually, I could see this as a function with two arguments, I gave it only one, the first one. Once this is done, I can provide the second argument. Okay, so what I say here is that the function applied to 6 and to 5. Now, consider the definition of my function here, okay? So this is when I expand this definition, I get this for n, fun n, 2 with a parenthesis. This is what I wrote before. Actually, you see that it makes sense to say that we can remove the parenthesis and it means the same. So the short notation is fun n to fun x to the body. And when you see fun n to fun x, you can even make it shorter and say fun n x to the body. This is a very short, the shortest notation. Okay, all of them work. They mean the same, but the shortest is this one, and I think I say it is more convenient because you see, okay, this can be seen as a function with two arguments, n and then x, which shortens that. Okay. So if you write all this together, I say my function with its two arguments, and you see that this 6 will be the value of n, and this 5, okay, will be substituted to x here. Okay, okay. You see them in the same order, and there is no pitfall. It is very convenient. So actually, this is a function of one argument, return a function of one argument, but very often we just want to see them as like a kind of binary function. But this is not a binary function which it is a unary function which returns a unary function, and this you can go on with 3, 4, 5 arguments, whatever. We don't need tuples. We could use tuples, but actually, in a functional setting, it's much more convenient just to say, okay, I only have unary functions. It is more uniform, and we can perform a number of interesting things. Okay, so I can check that it works. I get my 16 as expected. Okay, and I will finish with functional programming with the last example. Here it is a function which combines function as input and function as output. So I took a very simple example which takes a function from nut to nut and returns a kind of translation by one of these functions. I return the function which takes n and returns f of n plus 1. So you see, I could write it another way. I could write fun fn return this, but actually sometimes it is more clear to see my intention. My intention really to say translate one will be applied to this function, then to the and maybe elsewhere to that one function. I will play with, really want to play with functions, and at the end, in another part of my program, apply the result to some numbers. But if I want to just to talk about functions from nut to nut, you could mean some curves. You can draw the function. I see, okay, I see the curve of my function, and I translate it. I get another curve. Okay. Okay, this is okay. Here you see the example of a functional programming. Okay. Once again, you can write it. Fun fn returns f of n plus 1. That's the same. So it is just a matter of taste, a matter of presentation to explain the reader what is your intention. You can be more explicit like this or not. Okay, so I think you have all the material we need. So I needed to take much time on that because this notation, these habits of using parentheses and so on, the fact that n-ary functions will be used in this way, it will be used implicitly all the time. So it is necessary to start with that. Now, I will go to another part of programming, which is not programs, functions, but just data types. And we'll start with the simplest data type you know, which is enumerated types. Okay, so an enumerated type, it's a type where you say, okay, I have, for instance, 3 possible values. Okay, so an enumeration, it is something we have in many languages. So let us say how it is declared in Coq. So it is declared using the keyword inductive. So don't worry about this name, because when you see inductive, you may see inductions, so some kind of recursivity. There is no recursivity here, no need. We will see that inductive types may have recursivity, but we will see that at the end of the lecture. Okay, actually, the inductive types in Coq are the basic notion for declaring all data types. All data types, oh, sorry. So we also have co-inductive, but I will not talk about co-inductive at least today. Okay, but okay, basically, you have inductive types, and these inductive types are enough for everything. In particular, tree-like structures. But so at the moment, we don't see any tree, but we'll see very soon. Okay, so inductive is a keyword. Then the name of the type will define. So it means traffic light. So I call it TL color. Later, I will use the name color for an extended number of colors. So, I will use this one at the moment. And now we have also this here. So because actually in Coq, everything is typed. So this is not like in programming languages. We have a mathematical framework where everything, a uniform framework where everything is typed, including the types themselves. So I'll introduce a data type, and a data type. So typical name for the type of a data type is set. So we will see that we have, it could be something else, but this is the most basic. So I like to use basic things, not complicated things, and this one is very simple. And okay, I'll reuse it. So now I explain that I have 3 possible values, canonical values in this type. So the 3 basic values are green, orange, and red, and all of them have the type TL color. So if you know about OCaml, you can have this syntax also in OCaml now, but the usual syntax you have in OCaml is that you don't say stupidly that all of them are TL colors. But in Coq, things are more rich, and for the sake of generality, it is better to have the good habit from the very beginning. So at the moment, just repeat, all of them are TL colors, okay? Okay. So the feedback of Koch is here. So Koch says that you just define TL color. Koch will not answer that you also defined green, orange, and red, but that's the case. Actually, they are defined. And also, Koch defined a number of other things. We don't have to care about this at the moment. Okay, so a number of predefined functions. Okay, so the important thing is that T color is defined, and as it is defined, so all its components are defined. So these components are called. Oh, sorry, it is off here. Okay, okay. So maybe I should write this. Okay. They are called constructors. Okay, so I forgot to introduce this name. Okay. Yes, so okay. I told this at this place. Okay. So I said that these three names are called the constructors, the way of constructing, if you like, the constructors of the type. So I have three ways of constructing a value of TR curve. That's very simple. Okay, so no need to repeat here. Okay. So now the next construct, which is very important and which is present in all typed functional programming languages, so which is called pattern matching. So this is something who has to be that we will use all the time. Each time we will try to see what is to reason or to program on a data type. So we will use pattern matching. So so we will see an example, but first here is the syntax. So the point is that pattern matching provides a result for each possible case of a data type. So at the moment, I have a simple data type with only three possible values. Three ways of constructing it. So the three ways are green, red, and orange. So in general, the syntax of pattern matching is as follows. The pattern matching is match expression. So here I need to have an expression. But in the first example, an expression will be just a variable, but it could be anything, any expression actually. Match this expression with, and then I have a number of possible cases. Each case is separated, or okay, the first one is optional, but between each construct we need to separate by a bar like this, a vertical bar. And then you have an arrow. On the left-hand side, you have what we call a pattern. So at the moment, it will just. And on the right-hand side, you have the result corresponding to this pattern. Okay, so let us see an example. So, yes, the important point is that I have to look at the type of this expression, and according to the type, so the type has to be an inductive type. It makes no sense if this expression is a function, for instance. I cannot match against a function, but I can match against a color, for instance. Okay, any data. Okay, so this data has three possible shapes. Okay, so let us see this the example here. So I have a function next call which takes as input a TL color, and I declare that I will return a color here. So the definition will be a function because it is a function here. Okay, so it is a function of C which returns. Okay, so now C is available. So C is an expression of type TL color. Okay, this is the type of C. So C has three possible shapes. I give them one by one. If C has the shape green, my result will be orange. If C has a shape orange, so I return red. And if C has the shape red, I return green. So you get the idea. Just the order of the traffic light colors. Okay. So here you see I use the functional construct and a very simple pattern matching in the body of the function. Okay. So next call is defined and it has the type okay, here I announce the type. I could be lazy, but okay, here I was explicit. So now let us play. So first I can check that my function, sorry, here. I can check that my function has a type, has an expected type. So yes, so the answer is here. Now let us apply my function to green. So at the moment I didn't compute, I just check the type. So here it has a type TL color to TL color. Here the argument is green, it is a TL color, so everything is okay. So what I should get is the type of the result. The type of the result is here, so I expect to get a TL color. I don't know how much, which one I mean, but just is type. Yes, the type of this expression is indeed TL color. Everything is fine. Now let us try to compute it. And I get orange. Yes, the next color of green is orange. So everything has been computed as you would expect. Okay. Now let us make things a little bit more complicated. Later, I just present another strategy which can be used when I have only constant names which have been defined, like here. Okay, so I can use another strategy which is called compute. Okay, which is a common strategy. Okay, and it returns the same orange. So okay, in this case, no. Okay, CBN is able to deal with cases when you have variables, and compute is more convenient when you have only. So it makes a convenient. The only point is that you have a shorthand for eval compute in. So if you are lazy, you can say just compute. But compute will use this strategy, not CBN. Okay, there is no big CBN, for instance, up to my knowledge at least. Okay, so again, I can type compute this and get orange. Okay.
Sorry, one question. Can you explain the difference between CBN and compute, the two strategies?
CBN is called by name, so it is able to, it is somewhat more lazy. And compute, it is, I think it is a kind of callable value.
We can also try CBV. The less was CBV and compute. For this simple example, it doesn't make a difference.
No. Because my expressions are too simple. If you want, if you want to see, the differences, okay, I can take some risk. I make it simpler. Okay, here I get, okay, CBN says, okay, I don't compute anything. If I try compute, I don't know what happened. Yes, here, oh, sorry. Compute will expand the definition. CBN does not expand the definition. Here, compute expands the definition of next call.
Compute expand and then CBN?
CBN does not expand anything.
Ah.
He's more lazy.
He's more lazy.
Okay, and I guess that CBV would also expand the definition. Yes. So I think I don't know the difference between CBV and compute. Okay, look at the documentation.
Yeah.
Okay, I think there are maybe differences when you have variables, for instance. Okay. So now let us go to more interesting inductive types. So we have seen the most basic of them, which is enumeration of values, of simple values in some sense, green without anything, etc., etc. Now we can have enriched constructors. So I mean a constructor with something with it, decorated with something. Okay. So the point is that, okay, we will see, okay, on the example, but so we have, okay. I mean that here, sorry, here, the type is just the type I gave here. Now I will make something more complicated. You will see that the type of the constructor will be not just here, not just that, but it will have a type, similar to the type of a function. So it is, okay, it behaves basically like a function. So in OCaml it's a little bit different, but okay, in Coq can say it is like a function. Okay, so the idea is that, okay, let us see two examples. Here I will, okay, I have another example called color. Which is made also with three ways, three possible shapes, three constructors. One is just like before, a single color, which is called yellow. You see that the result is always color. It is something which is completely different of teal color. There is, I mean, there is no intersection. Forget about the notions, the set theoretical ideas about union, intersection, and so on. Types oblige you to make things always separated. Otherwise, you get a mess. Okay, completely separated. I would say universes, but universes have a special meaning here. Okay, so the point is that I always get color at the end. Okay, that's the point. I always get a color at the end, and okay, so for the one it is a color without anything. The second one, TLC, why? Because, yes, because it is traffic light color, which is, I think, what I meant. Okay, so it can take a teal color that I defined before, and when I applied this TLC to a teal color, I get a color. It is like a kind of correction, if you want. But okay, anything, think about this like a kind of decoration. I decorate a teal color with TLC and I get a color. Okay, and here I want to have grays and more or less gray. Okay, and here I use nut because I have nut. Okay, so I could have a slight gray or very dark gray, imagine, and I say that gray of 10, for instance, is a color. TLC of red is a color as well. Okay. Okay. So the point in here is that I have a choice between different constructors. Each time at the end I get a color, and in order to get a value, the real color, I need to apply the constructor to something, which it could be a teal color, or to a nut, or to nothing here. In order to have them. Here's an example. For instance, GR6, which is gray of 6, gray applied to 6. So you see, I use a functional application. Always the same trick we learned before. Gray applied to 6, a color. Okay? So let us see the next inductive type here. So this one has only one constructor called CP, like a color point. Okay, so the idea is that in order to get a color point, I need to provide three things. So again, this is like a function with three arguments. Okay, So I provide first a color, and then I provide a first coordinate and second. So you could imagine a plan, okay? And so let us say an example here. My CP here, it is also, I say that it's a CP applied to a color. See the color I got. Well, see, this color was obtained by applying TLC to the TL color red. Okay, TLC of red is a color. Okay, so this color can be an input of a first input of CP. Then I have to provide a number and yet another number. So, okay, first number, 2, second number. So you consider the X and the Y, for instance, okay, in the plan. Okay, all this makes a colored point. Okay? Using the functional notation. Okay, so again, so I could be more progressive. Here, Koch answers that color is defined with a number of other things. Similar for color point. Color point is defined. Okay. A keyword example. Yeah. So it's just to say another way of saying definition. Okay. But okay, I just want to make this definition very important. Just say it is an example. Okay, but it is a synonym. Okay, no, it does not. You could write definition, but okay, this is just something for mathematicians. I like to have different names for the same notion, but with a different intention. Okay. So GRI6 is defined, and as it is defined, it must be well typed, and the same for the next one. Did I check them? No, I didn't check them. If I could print, I will have all information, say, for instance, my CP, but I will just get the same, okay? There is nothing to compute, for nothing to, okay, I could also compute it, but, okay. So I just get what said my definition. So nothing new. Nothing new here. So now let us play with pattern matching. This is here where we start to have, and here I would like to have a blackboard. Okay, yes, because it is interesting to see inductive types and to draw them as trees. Okay, maybe I will have time to show another example if I run. Okay, maybe tomorrow then. Okay, so now if I want to write a program, for instance, I would like to return some net from a color point. Okay, so as before, so I take my function which take a color point. I have a pattern matching here which takes CP, and we see that CP has 3 components. So the pattern here has the same shape. It is the name of the constructor, and I have to give a name to my 3 components. So you could see that a kind of expression made only of, this is very important, this kind of expression here in patterns are special expression made only of constructors and variables. And the variable in some sense says that, okay, I will match these things against a real CP, a real a real call point, sorry, and by matching the against, I will say that C is the first component, X is the second component, and Y is the third component. Okay, first, second, third component. Okay. For instance, in this case, first, so I check that I have the right constructor at the beginning, okay, here, and then first component, this one, it will be C. This one would correspond, so X would correspond to 2, if I apply this function to this one, and 3 with, okay, so if I apply my function here to this example, I would get here 3. Okay. And okay, I can do more complicated things. I could have more patterns here. This is here. We can start to see the power of pattern matching. Pattern matching does not need to be of depth 1, I would say. I have here a pattern matching with more depth. Okay, so here I will match CP against, or I have no choice. Or it should always start with a CP uppercase because of the CP, but then could be constructed. So the two last are natural numbers. So I will not try to make to give something here, but here I can play because I defined my own color. So yellow is a possible color, you remember. TLC of something is a possible color, and gray of something is a possible color. Let me. Okay, I'll recall here. Now the possible shapes of a color are given here. Well, okay, just by looking at the inductive definition, I see what I could have. I could have a yellow alone. I could have a TLC applied to a TL color. I could have a gray applied to a number. Okay, so we try to put this at the top. Okay. I will try to play with my Emacs. Okay. Okay, I will have. Okay, I have my definition here. Okay. And on the bottom here, I have my. Okay, I have my definition. Okay. So you see here that I have CP applied either to yellow, like here, or to TLC of some traffic light color, TLC, or gray, etc. So if I had a screen, it's difficult. I will not try to draw with on Emacs here, but you have to imagine that you have a CP, and just under the CP a yellow, or here a CP, and under the CP you have a TLC, and under the TLC you have a TC. Sorry. Under the CP you have three things. So you have three branches. First branch, yellow. Second branch, on top of the second branch you have XY. Third branch, Y1. Okay. Here you have another pattern with first branch, which is itself TLC and TC under it. Second branch X, third branch Y. And here, same idea. Okay. So it's a pity that we don't have a screen, but maybe tomorrow I will draw if possible. Okay, and now the point is that in each case I catch what is inside my call point. Okay, for instance, in that case, if call point has this shape, okay, I will catch three things. I will catch the traffic light color, and we catch the Y, the X and the Y coordinates. Okay. And what do you want? Okay, I want to return a TR color. Why not? So in the first case, I want to return green. Okay, the example has no meaning, just to illustrate pattern matching. Okay, here I can use TC, and when I have a traffic light color, remember I had a function which was called next call. As I have a TL call, I can play with it and apply it to TC. And here I have nothing special, so I return red, for instance. Okay, and I can. Okay, I can compute. I can compute my function applied to my color point. So let us guess. My CP is here. My CP is here. Also, it is CP of that. CP of TLC. Okay, I am in the second choice. Okay, so I should return the next color of the TC. The TC is here, so I should return the next color of red. So I hope to get The next of red is green, I think. Green, orange, red, and go back to green. It depends on the definition of the next color. Maybe you are red, and you have to remember the definition. But I think it was this one. Okay, so I get green. Okay. So here you learn the very powerful mechanism of pattern matching. Also, okay, so maybe we get my single thing. So this is something important, which is, so this is not only for Coq, it is available for OCaml, for instance. So Haskell has a different syntax. OCaml syntax is similar, but the point is the mechanism is very powerful because in each case, okay, this is explained here. Sorry, I will go here. Okay, this is what I said here. For instance, TC has this name only sense here on the right hand side of this arrow. TC does not make sense here. It does not make sense there. I cannot use it. Okay, I could use X. I could use X here, but I cannot use X1. I cannot use X2. So this makes the programming very secure. If you compare, for instance, to Scheme or Lisp, or to talk about other functional programming languages, you have to, when you have a structure, the way you proceed is to say, okay, I make a test. You make a kind of if this list is not empty, something like this. If the list is empty, then return something. And if it is not empty, then I am allowed to try to compute the tail and to compute the head. Here I have the tail and the head, or it is not tail head, but there are the components of my thing, the component of my argument CP. I have them for free, and I have all of them. I have the head, the tail, and all of things, and there is no possibility of mixing things up with the other cases. Each case has its own logic, its own way of proceeding, and they don't. Okay, there is no possible confusion. So this is really type safe and efficient, moreover, and you don't have to recompute from the beginning. You have to do, or you don't have to recheck if I am in the right case, or if you don't want to check, you don't have to prove that you are in the right case because you already performed the check. So this is something which is very powerful in functional programming. This is something which is very often understated, but it is which is what's one of the very basic mechanism of functional programming, which is very important. Okay, let me correct this. So unused variables can be replaced by a joker. So the underscore. So let us see the next example. So I call the junkers. So here I match a CP against, so this one, this is like before. So I can use TC. I don't use these components, so I can put a joker here. Okay. And what I say is that in all of the cases, so this is like, I could put a name here. I could say, okay, against another CP or A or whatever, Z or whatever, or just underscore. In a way, I don't use it in a return orange. So what you have to understand that in this situation is that the pattern matching will check, okay, if I am in this situation, I return that, including if it is a yellow, okay? So, okay, so I'm writing this way. So even for a yellow, which is defined before, here I followed the order of the definition. Here I don't follow the order of definition, but I say that even for a yellow, the result will be an orange. Okay, so here I compute with a gray. So an orange, yes. if I compute, okay, let us try yellow here. I expect an orange. Yes. Sorry. Yes, orange. Okay. Let us see what happens if I print jokers. Let's see what how Coq prints it. Okay, it prints the same way I wrote it. So according in former version of Coq, I think he printing things maybe in a more explicit way, but they made progress, and they leave it very close, like in my original definition. There are options for saying printing all, but okay, I will not have the time to make these fun experiments. But okay, so print adds no information. Actually, I think that Coq, okay, it's possible. I'm not sure actually. It depends on how the algorithm is translated inside. Okay, so now let us look at the next power of inductive types. We have seen enumerated types, just constructor without information. Now we have seen constructor with contents, and now we will see that the contents can be recursive. What do you say? Okay. I say that the constructors can also be recursive, but we will discover that later. Wait a little bit. So let us turn to something else, proving theorems. We change a little bit. Okay, what kind of thing we can do? Okay, let us prove this thing. So I would like to prove very simple theorem, which are just equalities. So how do I prove theorem? So I write theorem. I gave it a name. Everything has a name, and I say that the statement of my theorem. I say that the next color of green. So the color of green is orange, and the next color of orange is red. So I expect to get a red. Okay. So the good practice is to write proof here. You can. It is not mandatory, but it is nicer to write it, and then you get you see this window. Is it large enough? Okay. So here you get a series of a bar, basically. It is like a big bar, nothing on top of it at the moment, and you get the conclusion to be proved. Okay, exactly my statement here. Okay, and so we'll see how to prove this. And how to prove this? Well, okay, the thing to do is to compute what is here. I will compute the next call. So this is like the CBN we have seen before. Here I am a little bit more precise. I say that I want to compute only, well, this is the only thing actually. I want to compute and I allow Coq to reduce only the next call function. I could have other functions, but only this one. Here it makes no difference. So just to show that CBN has a parameter between square brackets, and I say, okay, let us compute this with this function. Okay, and after computation, I get red. And here I'm very happy because I have red is equal to red. So you could see, okay, this is a very basic things about equality. When I have the same value on the left and on the right of equal thing, I am finished. Right? Okay, so okay. Okay, so that to say that that I use CBN with an argument. Okay, so it is finished. And so how do you prove this kind of thing? You use another tactic. So we will see later how it works, what is behind that. But at the moment, it is enough to say, okay, reflexivity. is when you have exactly the same thing on the left and on the right of the unequal side by reflexivity. Okay, so no more goals. Is I have proved my first big theorem. Okay. Now, okay, if you open a book of theorems, lemmas, remarks, facts, whatever, I don't remember. So, okay, so ASCOC is expected to be used also by people with a mathematical mind. They like to have their own keywords. So the same keywords can be used also in COC. Keywords? Sorry. Okay, so okay, you can use other, but it makes no difference. It is just a synonym. Okay, even that we have seen before. It is when it is not really a theorem, but just something too simple to be considered as a theorem. It's just to say, I expect that by example, the scholar of something returns something. Okay, maybe it's okay. You could see that an example. Okay. So let us see. Okay, a last thing is that at the end of a script, you have to write QED because you have okay, like here. I write my QED here, so I finish the proof. If you don't do this, you have a kind of standby. I don't know how to explain this. And at some point, you will have a strange feedback of code. So don't forget here when you have no more goals, always write QED. Don't forget this. Okay, so a tactic is a command which allows you to progress in a proof. So basically, when you write a proof, you progress, you have a goal, and then you have new goals. You say progressively that things are progressing expectedly. And okay, so the two tactics we have seen before are CBN and reflexivity. Okay, okay, so I'll just put that. Now, variables again. Okay, so I can state a theorem which talk about a variable, something, okay, we do quite usually, okay? So, for instance, reflexivity works not only between identical constant expressions, but also between expressions with variables. For instance, you could say that say 2 plus x is equal to 1 plus 1 plus x. Just an example, okay? I have a variable, but anyway, I expect that they are equal. Okay, so in COC, it makes sense to talk about expressions with variables, not only, especially when we make proofs. Okay. So again, let us open a section. Here it was explained before, and I have a variable C, which is a T alcolor. Okay. Intuitive meaning, but okay, that is like we had already that earlier. Nothing new. And okay, I just want to prove that C is equal to C, because it's not very interesting, but just to say that I am able to do that. Okay, actually I have a constraint. On the two sides of the equal, I should have expression with the same type. I will not be, okay, if I want to write a 2 here, okay, okay, does not make sense. It is not false. It is not provable. It is not even, I cannot even state it. It does not make sense to state this. Okay. So, sorry. Yes, x. X was not found. Okay. Okay. C is equal to C, no problem. Okay. And okay, the new thing here is that my goal is like before, C is equal to C, but I have an environment here where C is declared. So on top of the bar, you just have actually what has been declared. Okay? The word where you are in a world where some C exists and it has a type given here. Okay. So we have this by a hypothesis stating that C has a type this, a type color. So I have to go here. So proof, and this, of course, reflexivity. So nothing difficult here. QED, don't forget. Well, C is still there. Okay, so I could check. Okay, let us finish here. Okay. I am very okay. I can even check that. Well, actually, you see, I stated a theorem, and Coq is okay for saying that this name, is a statement for a name which has this type. Okay, but the type in that case is the statement of the theorem. Okay, so we will talk more about that later. Okay, and then we close the section. Then, yes, so C, for instance, now is no longer available. Okay? C was available inside the section, but outside the section, no C available. Scope mechanism. Okay, so once again, I can try to make this kind of computation. But it was because I put a fail here. So it is interesting. Yes, already here I had this. So it is interesting to have this because for me as a teacher, because I want to show something which is expected to fail. Okay, and if just put this, I'm blocked. I cannot finish my demo. Okay, so I say no problem. I expect this to fail. Okay, and the command has indeed failed with blah 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 with the following result. Okay, for the following reason. And typically here I made a typing error. Okay, a type error, and let us now go to the next important thing to know about equalities. So for equalities, you have two things to know: how to prove them. This is by reflexivity. And another thing to know is how to use them. What happens if you have an equality? For instance, here you have the equality C is equal to red, and later you have something which talks about C. The thing you would like to say, but if C is equal to red, I should be able to replace C by red. This is what rewrite says. Okay, we will see later how it can be how it is defined inside Coq. It is actually not primitive, but for at the moment, just use it intuitively. It is not that difficult. So again, I have a variable C, TL color, and a hypothesis saying that C is equal to red. Okay, and I give it a name. C is red. Now, intuitive meaning, So I say that is red is somewhat like an unknown proof of C is equal to red. Okay. Let us see what happens when I try to prove a theorem. For instance, here I would like to prove that the next color of C is green. Okay. So here must be the next color of C is equal to green. And what do I have in my pocket? I have that C exists. By first hypothesis, C has the type TL color. Second hypothesis here is it says that C is equal to red. Okay, so you see the uniform way of Coq for displaying that C colon TL color and C is red colon C is equal to red. Okay, uniform way for displaying that. And let us go to the proof. Okay, and how to exploit this hypothesis. And if I try CBN here, nothing will happen. CBN, even the most powerful, okay. I get nothing. CBN, maybe I guess that CBV maybe would be more. Okay, CBV provides you more information. Global value. CBV, actually, what does CBV? I can explain you. Here I have a function definition, and this function, if you remember its definition, it says, okay, I provide C, and then I will perform a pattern matching on C. So CBN says, okay, I'm too lazy, I don't want to do anything. But CBV starts the computation. It replaces the C of the definition by this C, but we have nothing more. It is some C. Okay, I don't know that C is not equal to red by definition. It's not different. If I said C, I define C to be red, it would be different. Here it is only, I have a proof that C is equal to red, that it is different. It is not a definition. It is just something which could have been proven in some complicated way. So it is something which is weaker, actually. So, okay, so I know that C, okay, is at the end equal to red, but by computation, I cannot go further. Okay, okay, but I see that I have, okay, you can see that if you know more about C, if you can replace C by red, for instance, then we see that the computation could be performed. Okay. In order to do that, I'll say rewrite this hypothesis. Rewriting this hypothesis will replace C by red. This is allowed using the tactic rewrite. Without the rewrite, nothing will progress. Okay, so I can do this here, and then by also so the computation is instantly immediately performed. So the previous one, also, I can remove that. That's the same. Huh? So next call of C is equal to green. Is it equal to green? Now let us replace C by red. Ah, okay. Now I perform no computation. I just replace it. But now I can compute. So this time either the CBV or the CBN will do the job. Okay. So CBN will reduce. Okay. And then next call of red provides green like before. And now I can finish by reflexivity. So what we learn is that in this situation, I have a proof of C is equal to red, but I don't know the proof. I know that the result is that C can be replaced by red, and replacing C by red is performed by this tactic. Once again, this tactic is something which can be explained in more elementary ways, but okay, at the moment, just use it. We consider that rewriting is something simple enough to be understood intuitively. I think that tomorrow I'll try to explain it a little bit. Ah, okay. I think, yeah, okay. So, my advice is try to download the file on my website, because actually the end of this file is a series of, okay, well, the things I explain on the file, and basically there are some exercises for you to be performed. So try to progress by yourself as far as you can. Okay, it should be very easy, basically. And I have a second file on my website. Maybe we can show here. Okay, so another example which makes a deeper use of inductive types for AST. Well, anyway, I will go back to this example tomorrow. Don't worry too much. The thing I want to say is that at the end of this file of today, we have, so here we have homework, but okay, we will start the homework before. You have here, yes, you have an inductive type which is recursive. So it is very interesting because this type is okay. I think you can understand what it is. It is a binary type with colors at the leaves. Okay, and you will have will try to by yourself to write a function, a recursive function. It is explained here. You can make a very simple recursive function which reverses the tree. Okay, so you see the function needs only 2 lines. Okay, and you can prove very easily, if you understand what is before, you can prove that the reverse of the reverse of a tree returns the tree itself. Okay, so basically you try to make the proof as before. So you need you have to discover the tactic destruct, which is how to reason by case. But in that case, you have to you will see that destruct is not enough. Reasoning by case is not enough, and then you have to make reasoning by induction, what we call structural induction. So it is explained. Okay, so basically, each time you have a recursive function, the corresponding proof mechanism is structural induction. So don't worry, I will explain this tomorrow. But if you start by yourself before, it will be much easier. Okay, so my advice is start this one, and if you find this too easy, and expect that we'll find this too easy, then go to the second file, and you will see more interesting inductive trees for AST, because in the sequel of my lectures, I will explain how to reason about abstracted trees, so like binary trees, but a little bit with more constructors. But it doesn't matter. We can very easily make interesting exercises. Okay. Okay. So try by yourself. Tell me if you have questions. You can write to me also. So you can find my email on my website. Okay, so if I go back here, okay, so you can click, but okay, you have to type carefully first name dot name. So sorry, at you. So not only my name is a bit long, but also my institution is long as well. I'm sorry about that. The six, the dot, the tiret of the, how to say, so this symbol here. Hyphen. Okay. Yes, this is the small hyphen. Okay, small hyphen, one here, a second here, and then a dot. Of course, this is one is usual. Okay, or maybe okay, I can type it. Okay, I write it here. Oh no, not here. Maybe in this one. In this one. Okay, I will write here on the top. Okay, I write my email. So François.Monin. Okay, so we were here in French. We have a Cedilia, but not, of course, in the not at this place. It's easier at Univ Grenoble Alp hyphen. Okay, I update. So okay, so don't hesitate. I'm here to answer your questions. I prefer you to ask questions than to keep stuck. Okay. Okay, so I will update as soon as possible.
Okay, thanks.
Okay, thanks for attention. Yes, if you have any questions, don't hesitate. Maybe it's too easy, I don't know. Maybe there were questions in the room. The chat of Zoom or the chat of
这个就这样吧，就问题你先记下来，完了以后你发给这个教授，下节课他再讲一下。因为有好几个人，我们就不一个一个回答，下节课再回答，好吧？如果他还不明白，或你有他们
I should ask in a positive way. It's better.
今天稍微有点晚，12点多，然后今天就结束了，有问题的话1:30才来解释。行，好吧，那我们今天就结束。
To everyone, is
好
okay.
好。
Did you see the? Yes.
What?
I don't know if it is.
Yes, they have some questions, but it's better that
Maybe in the.
we'll send you the questions and then you can explain tomorrow.
Okay. Okay. Fine. Thank you.
OK。那你跟线上说再见，线上同志们，我们去吃饭去了。
Yes.
OK。
Time to have lunch.
Yeah, thank you.
Okay, so I try to end the meeting. Yes. Don't know how to do that. Maybe.